All right, today for Algebra 2, we have complex numbers, section 5.5. I'm sorry about it being 3 pages separate. That's why they're all stapled. It's not as intimidating as it looks, I promise. I just pushed the wrong button on the printer. So our objectives today, though, are to graph complex numbers on a complex plane. It's not as complex as it sounds. 2, to find the absolute value of complex numbers. 3, simplify some powers of I. 4, add, subtract, and multiply complex numbers. And 5, always the last one, is to solve those real-world applications involving complex numbers. So when I get back tomorrow, we will probably take some time and watch a YouTube video about creating some fractals with complex numbers. I know you guys were asking, like, when do we actually use these in real life, and I couldn't really tell you about the imaginary numbers. So there are a couple cool YouTube videos, and you could look them up. And you could look up this phrase even and find some really cool things about creating fractals with complex numbers. But if not, like I said, remind me tomorrow and we'll watch some of those. So first up, a complex number, which is z in your notes, is a number that can be expressed in the standard form z equals a plus b times I. All right, so where a and b are elements of the real numbers and I is equal to the square root of -1. We talked about that a lot last week. All right, so complex numbers can be imaginary numbers. Okay, so those are in the form of a plus bi, where b is not equal to 0. And then you can have pure imaginary numbers, which are in that same form, a plus bi, but this is where a equals 0. Okay, so that's just where you have bi. So all of these kind of fall in the complex number system. So let's look at this complex number system. I have this awesome chart down here. So complex numbers, that a plus bi. So first up, we have the imaginary section over here. Okay, so all of these are imaginary. Okay, so this is where we have a plus bi and b is not equal to 0. So here, -2 minus I. So mind you, b here would be equal to -1. Okay, we don't see it, but it would be. Then we have 3/5 minus 9i. So a would equal 3/5. It can be a fraction. And our b would equal -9. Then, sorry, I threw my marker at the board. Then we have the pure imaginary numbers. Okay, so that's when we have 0 plus bi. So there's really no a. So just the 9i, the 3i, 7i, any of those. And our last section, these are the real numbers. Those are ones we really focus on and talk about all the time in our math world or in our lower level math. So this is when we have the a plus bi and b is not, or b equals 0. Okay, so because b equals 0, we really have a plus 0 times I, which just leaves us with a. So that is any of those other numbers that we usually think of in our number system. The square root of 13, -15, 3/5, 23. Okay, because b equals 0. So there are, in real numbers, there is no imaginary part to it because it's equal to 0. So together, the imaginary numbers and the real numbers form the complex number system. Okay, because that's what we have here, is the complex number system. It's the imaginaries and the reals. All right, so let's move on to graphing. Complex numbers can be graphed in the complex plane. Okay, so we're going to graph the real component along the horizontal axis. So if you notice, this is the complex plane. The real coordinates took the place of the x-axis. And then we're going to graph the imaginary part of it along the vertical axis. So if you look at where we usually have y, there's an I up there. So if we look at this number, z equals -3 plus 2i. Okay, we're going to graph the horizontal the real component, so this negative 3 here. So we come back from the origin, we come back negative 3. And then we take care of the imaginary on the vertical. So from there we go up 2 to put our point. So this point is negative 3 plus 2i. That is that point right there. So instead of having an x and a y coordinate, that's the part that's different, is we have this number, this z equals. Remember, because it's in that form, a plus bi. So the a part is graphed horizontally, the b is graphed vertically. All right, so let's move over to page 2. Okay, so the absolute value of a complex number or a modulus, z, equals a plus bi still. So the absolute value is the distance from the origin to its graph in the complex plane. Okay, so if we look at this, right, we graphed this point, we came over 3 and we went up 2i. I was like, my yellow's not working. Okay, but in order to get that distance, because it's not, that distance is not just straight from 0, it's a diagonal. So we have to treat it as like we're looking for this diagonal distance. Okay, so the absolute value of z. Okay, so in order to do that, we're finding the absolute value of z, okay, which is the absolute value of that quantity a plus bi, which means we're going to take the square root of our a value and square it plus the b value and square it. It's a lot like the Pythagorean theorem because, again, we're looking at this as part of a triangle. Okay, it is that hypotenuse of a right triangle. All right, so if we look at this example, z equals, or the absolute value of z equals negative 3 plus 2i. Our a equals negative 3 and our b equals 2. These are the numbers that we plug in, right? So we have the square root of negative 3 squared plus 2 squared. So we end up with a square root of 9 plus 4, which is the square root of 13. So this absolute value, right, right here, this distance from the point to the origin is the square root of 13. That's its distance. All right, so example 1 says graph and find the absolute value. Okay, so here is, I've started the work for us. We just have to go back and graph it. Actually, I've done all the work. So here's our equation, 4 minus I. So in this case, our A is 4. Our B is negative 1, because this is the same thing as 4 minus, or 4 plus, pardon me, negative 1I. So my B is negative 1. So when I go to plug those in, okay, so the absolute value of 4 minus I equals the square root of 4 squared plus negative 1 squared, which is the square root of 16 plus 1, or the square root of 17 is the distance. But let's graph it. Okay, remember, we graph the real number component on the horizontal axis, so it's a positive 4, 1, 2, 3, 4. And then I graph my imaginary, so my negative 1, on the other one, on my vertical axis. So let's try again. So I come over 1, 2, 3, 4. I'm going to go down 1, and I'm going to put my point right there. Okay, so that's my graph of 4 minus I. And, okay, my distance, my absolute value, is the square root of 17. Okay, so that's the distance from that point to the origin. Okay, so let's look at the next one together and graph it. So we're going to go negative 2 and then negative 3. So I'm going to go negative 2, negative 3. So this is negative 2 minus 3i. Okay, so to find my absolute value, remember I'm looking for this, whoops, got my eraser. I'm looking for the distance from my point to my origin. That's my absolute value. So let's solve it. So first, what's our A equal? Good, -2. And what's our B equal? Perfect, -3. So the absolute value of -2 minus 3i equals the square root of A, so -2 squared, plus B, -3 squared. Sorry, I almost wrote B there. Still looks like B, except it's not. Okay, so let's do the math on that. -2 squared is, good, it's 4, plus what's -3 squared? Excellent, it is 9. So the square root of 4 plus 9 is, good, the square root of 13. So we have the square root of 13 there is the absolute value. So again, we're just plugging these in, like picking out the A and the B, plugging them into the formula and solving. It's not too terrible. I'm sure Ethan just said yet, or maybe it was Brandon, but. All right, let's move on to adding or subtracting, to add or subtract complex numbers. You're going to add or subtract their real components and then their imaginary components. It's like combining like terms, okay? So I've got a little bit more of an explanation there. So if z equals a plus bi and w equals c plus di, then z plus w is going to equal a plus c. So see, those are the real components. And we're going to do the quantity b plus d times I. So we're just adding the imaginary components. It truly is combining like terms, right? It's the same result. And if it's subtraction, okay, notice the subtraction goes inside here, right? It's a minus c plus the quantity b minus d, combining like terms. So if we look at this example and we simplify it, my like terms are 3 and 5, and I'm adding. So I'm going to have 3 plus 5. And then my other ones, my imaginary is 2i plus -4i. I'm going to add those together. So 3 plus 5 is 8. 2 minus 4 is -2. And there's my answer. It's just like combining like terms. So let's try one together. Okay, and the quantity 5 minus 3i minus 2 plus 6i. So here we're going to do 5. Notice it's subtraction. So I'm going to have 5 minus 2 in there. Okay, and then I have a -3i, so I'm going to put plus -3i. Now remember, it's subtraction, so I need to bring that over, minus 6i. I need to distribute that just like I always have. Okay, so when it comes to combining the like terms, 5 minus 2 is 3, plus -3i minus 6i is a -9i. Now you know we take this one step further always and simplify it, and we would say it was 3 minus 9i. We wouldn't have to leave the addition in there. But just so you see it clearly. Okay, perfect. Only one more page to go with these complex numbers. It's a glorious day. All right, so the last part is to multiply complex numbers. Okay, so one thing to remember is that I squared equals -1, because we're going to simplify and we're going to need that later. So to multiply complex numbers, you're going to apply the distributive property or the FOIL method just like always. You write the result in standard form, that a plus bi, by combining like terms. Make sure you substitute -1 for I squared when you have an I squared. All right, so we're going to dive right in. I didn't do any of these examples for us, so we could dive in. So we're just going to, on the first one, distribute. 5i times 3 is 15i. 5i times 2i is going to be plus 10i squared. Okay, I have this I squared, which I need to replace, substitute in a negative 1. So this is going to be 15i plus 10 times negative 1, which means it's 15i minus 10. Oh, but I don't have it in standard form. Yikes. Let me back that train up then and say it's going to be negative 10 plus 15i. This is that standard form, right? The a plus bi. So make sure you don't forget to do that. With b, okay, we're going to FOIL for b, okay, because we have two binomials. So 4 times 2, the first is 8. The outside 4 times 3i is going to be plus 12i. Then we do the inside. So it's negative 2i times 2. It's going to be negative 4i. And the last, negative 2i times 3i is going to be negative 6i squared. All right, then we combine like terms, right? Positive 12i and negative 4i. So we have 8, positive 12 plus and minus 4 is going to be 8, so plus 8i. We also have this I squared, so let's go ahead and take care of it. So it's going to be minus 6. I squared means we replace it with a negative 1. And I squared is equal to negative 1. All right, so then we have 8 plus 8i. Negative 6 times negative 1 is plus 6. We've got more like terms, right? 8 and 6 are like terms. So that's going to give us 14 plus 8i after we combine our like terms. Remembering that I squared is equivalent to negative 1 is going to be very helpful. Okay. All right. Then we have some sum of squares. So let me go up here, the sum of squares. Okay, so we have not had the sum of squares before. It was not possible without a complex number. We've had the difference of sums and the difference of sums. We've had the difference of squares and some things, but never the sum. Okay, so the sum of squares, when we have a squared plus b squared, factored into a product of complex conjugates, okay? So this is the deal. When we have a squared plus b squared, it equals the quantity a plus bi times the quantity a minus bi. So we have not practiced that one yet. So in example 4 and example 5, we're going to use this both ways. In this case, in example 4, we're multiplying. So we're given what it looks like, right? We're given that binomial stage. Okay, so we have our a is 3 and our b, right? The I is here. So our b is the 5 times the square root of 2 is our b value. So when we're multiplying it, we're taking the a squared, so 3 squared, plus, and our b squared, which we said our b squared was 5 times the square root of 2 squared. And then we're done. That's it. We just have to put it into the sum of squares. Just following that formula. In example 5, it's different than that. Okay, in example 5, we're given the sum of the squares. Okay, we're given the sum of the squares, this part, and we have to factor it into the last part. So we still need to know what our a is and what our b is. Okay, so 4 is a perfect square. So what number is that squared? 4 is equal to 2 squared. So my a is what? X. So in this case, a equals x, and what's our b equal? 2, because this is the same thing as x squared plus 2 squared. All right, so if we're going to factor this, we're going to take our a, which is x, and we're going to have it plus 2i times the quantity x minus 2i. And we're done with that one. Okay, that last part for the last objective, simplifying the powers of I. Okay, so if you notice here, I've got I to the first equals I squared equals -1. I cubed equals a -I, because that's the same thing as I squared times I, which is -1 times I. So it's -I. And then I to the fourth is a +1. Okay, because it's the same thing as I squared times I squared, which is -1 times -1, which equals a +1. Okay, so these things repeat each other all the time. Every fourth one, this pattern repeats. So to simplify the power of I, we can divide the exponent by 4. And then we're all left with +1s. The remainder will give a power of I equivalent to the original power. So we're looking at the remainder. So if we look at this example 6, it says simplify I to the power of 59. I do not want to have to follow this pattern of 4 here all the way to 59. Okay, so that's why it says to divide the exponent by 4. So that's what we did. The exponent was 59. 59 divided by 4 was 14. So what that is saying is that we have that I to the power of 4 14 times. But remember, I to the power of 4 is 1, so it doesn't matter. That's always just equal to 1. I to the power of 14 is equal to 1. The part that truly matters here is the remainder, because that remainder means that this is I to the power of 3. And I to the power of 3 over here is equivalent to -I. So in this case, I to the 14th power times -I, so I to the 14th is just 1 times -I, leaves me with -I. So to find that pattern, or like to find the number that really matters, because it doesn't matter what this is, it's always just going to leave you with 1. Doesn't matter if it's I to the power of 72, or or if this number becomes 72, it's going to equal 1, because any 1 to any power is still itself. It's the remainder that's important. So you will want to memorize what the values of I are equivalent to. You will want to memorize that. All right, good luck on your homework. And I think you guys will do awesome. Just take your time and use those formulas. And I will see you tomorrow.